Now we are going to investigate the curious case of double polarizers. In optical spectrum, it is more known as three-polarizer paradox. But since microwave transmitter and receiver we use here are basically already have linear polarizing characteristics, two linear polarizers are enough to replicate the experiment. The main ingredient of the polarizers are copper wires which are aligned 5 mm apart. The frame is shaped as octagon to make it easier to rotate in the multiple of 45 degrees. The edges of the frame is labeled by numbers from 0 to 3. Due to reflectional symmetry, the numbers are repeated. Let's start with usual setup, where transmitter and receiver are oriented vertically, and the distance is adjusted to get maximum scale reading. When a polarizer is placed between them at position 0, the reading goes to 0. At position 1, the reading increases, but the value depends on the distance between polarizer and receiver. At position 2, the reading increases to nearly maximum. The case for position 3 is similar to position 1. This is caused by interference with partially reflected microwave which creates standing waves between polarizer and the transmitter, as well as the receiver. This effect doesn't occur when the polarizer completely blocks or passes the microwave. Let's put the first polarizer at orientation number 0, which makes the wires vertically aligned. The reading goes down to 0. The second polarizer is then added closer to the receiver. No matter how it's oriented, the reading stays at 0. Now the first polarizer is rotated 45 degrees to the right, and its top side is labeled by number 1. The receiver shows 40% intensity. But if the polarizer is moved closer to the receiver, the reading seems to oscillate. This is caused by interference with partially reflected microwave which creates standing waves between polarizer and the transmitter, as well as the receiver. Now the first polarizer has been turned to octagonal side number 1. Its position is set to get highest reading, which is 40%. The second polarizer is then placed in front of receiver, oriented vertically, which makes the reading down to 0. When it is turned to position 1, the reading goes up to 40% again. At position 2, it goes up even further to more than 50%. At position 3, it goes back down to 0. Now the first polarizer has been turned to position 2. The receiver shows maximum scale intensity. When the second polarizer is at position 0, the reading goes down to 0. When it's turned to position 1, the reading goes up to 70%. At position 2, it goes to maximum scale. At position 3, it's back to 70%. Slight movement can make it down even further due to interference. Let's see how much interference effect is produced by the polarizers in this orientations. It seems quite intense, so the reading can go down to near 0 during destructive interference. Now the first polarizer has been turned to position 3. The receiver shows only 30% intensity. Ideally, it should show 50%. The discrepancy can be attributed to the misalignment of the conductors in the polarizer, or partially destructive interference. When the second polarizer is at position 0, the reading goes down to 0. When it's turned to position 1, the reading stays at 0. At position 2, it goes to above 40%, which is higher than the reading without second polarizer. At position 3, it's back to 30%. Let's recheck for position 2. The reading is very sensitive to slight displacement or misalignment.